Introduce Epifanio Virga from Pavia, who, among other things, has the honor of being the Microsoft Visiting Fellow in association with this particular program. Cool. And he's going to talk about order tensors of equilibrium phases.
Well, thank you very much, David. And I'd like to take this opportunity to thank the organizers and my hosts here for what I hope is going to be a very pleasant 6 months stay. I stay through the whole program, and from what I already learned, it is going to be a very active and hectic time of my research. So I had been asked to prepare a kind of blend between a lecture and a tutorial, and this I think has been a very demanding task, and I think I've worked on these 2 lectures I'm bound to give more than I had worked on any other lecture in my previous career. So presumably and I've changed the presentation several times. The last change occurred at 9 o'clock this morning. This is the reason why I was late. And usually in my mind I try to have a complete picture of what is going on, but this time, due to the many changes I made, I don't even know what I'm talking about. And sorry about that. And so, I mean, some of these lies will be a surprise also to me. I try to interpret them as much as I can. Well, thank you, Peter, for the effort you forced me to make. Well, what I'll try to do, in this mixed lecture and tutorial effort, I'll try to fill the gaps between some known territories. And I'm very indebted to Tim, who actually alluded in his lecture today at some of these territories that need to be bridged. And of course, I will not be able to bridge these territories, but I hope to be able just to locate and design the lands that need to be bridged. To my knowledge, at least, this is work to be done, and I hope that this will serve the purpose of initiate some discussion and comparison about different views. So I'll start. Well, usually the outlines at the beginning of a lecture are quite useless, but not in this time, because they serve the purpose of reminding myself what is going on. So molecular interactions will be my first start. I'll try to describe in mathematical terms what might be considered a kind of paradigm of molecular interactions and how they enter a larger picture. The idea is, as you can imagine right by this outline, the idea is to try and bridge the microscopic understanding of our molecules interacting between them, give rise to this common organization that would produce liquid crystal behavior, and the macroscopic continuum description which has been evoked already in Tim and Oleg's lectures. And then we focus on quadrupolar approximations, and we give examples of apolar interactions. I mean, polarity is going to play a role, and as it did actually at the beginning of the story, when people thought that the interaction between dipoles and molecules could be at the basis of the liquid crystalline behavior. And Tim already reminded us that this is not the case. And I will introduce the preliminary description which is behind the Landau-Desjardins theory, which is based on the quadrupolar tensor theory, tensor representation, Q tensor, and it is called the quadrupolar tensor theory. And if time permits, I will come back to this idea of interpolating Hamiltonians, which actually is related to the failure of the dipolar interaction to describe liquid crystalline behavior. But I mean, this only if time permits. All right, we come back to this basic idea of molecular interactions, and there are different definitions in literature of order and disorder, and how they differently, how molecules are differently organized in space. But this is a kind of a key argument. The subject of order parameter is pervasive in soft matter. I mean, we know, and we have already been exposed to this notion in Tim's lecture. It is a kind of descriptor which has to be defined in a better and a more appropriate way. It is a kind of descriptor of the tendency of the molecular arrangement to surface at a macroscopic level. And this is a common feature of all soft matter. And to my taste, maybe I think that to date, the most convincing systematic way of introducing order tensors is what Claudio did in his PhD thesis, or I don't know, I mean, several years ago, 1979, and this is a nice. Well, I didn't mean to be. All right, but I think it is 79. When no, not the 1979. All right, the idea is in Claudio's approach is that the proper way to define order tensors should arise from the properties, trying to be vague deliberately, from the properties of the molecular distribution function. So this is the idea. I'll follow, of course. I read the paper and I enjoyed it. Actually, it is a book chapter. And I enjoyed it. But I'll try to take, inspired by his treatment, I'll try to take a different, a slight variant to this avenue, which is based on the properties of molecular interactions. So, what do we mean by that? Well, the idea is, the first item in this intellectual construction is that we start from the Hamiltonian interaction between two particles. All right, I deliberately say two particles because they might be two molecules, they might be molecular aggregates, they might be colloidal particles. I mean, the two the entities that are the basic building blocks of our theory. And of course, this is a scalar function which depends on the relative position of the two particles. It depends on the state of the two particles. If the two particles are complicated by different conformations, it might depend, well, the state depends on the conformation of the two particles. But it also depends on the relative distance and on the vector joining the two centers of mass. Of course, the more you think about it, the more this complicated the picture becomes. But of course, here we are to simplify things, not to make them more complicated. And so one way to to simplify them is by imagining a new quantity which we call the average Hamiltonian. The average Hamiltonian is this pair, which is also called the pair potential. It is this Hamiltonian which describes the interaction between these two entities once it has been averaged into the intermolecular vector. So what we want to do to get at the end is a function that depends only on the relative orientation of the two molecules in case the state is described only by the shape of the molecule, which is thought to be invariable. So for the moment, we rule out all roles, the role that different conformations may have. Of course, in this ideal and conceptual average, there are two ingredients essentially. One is you need to make some assumptions on the distribution of the intermolecular vector, and this is a quite a sensitive assumption, because depending on the degree of anisotropy that you insert into this distribution, you might get different answers when you take the average Hamiltonian. And to keep things as simple as possible, we usually imagine, and most people usually imagine, that the distribution function in the intermolecular vector is completely isotropic. Of course, again, as I said, it is not a mandatory assumption. It is a simplifying assumption. One should be aware, in constructing a mathematical theory, one should be aware of the simplifications that have been introduced, and one should also be aware of the fact that by changing one single approximation of the theory might be dramatically affected. So I'm just pinpointing the major assumptions. And of course, the second thing that one has to bear in mind is the fact that when you take this average and you are averaging in all different relative positions of the two particles, you are also imagining of bringing together the two particles up to the point when they coalesce and collide. And in doing this, of course, the shape of the molecules will play a role. This often is fully considered in the purely entropic approaches that have been recalled today. Clearly, if you imagine that the only interaction comes from excluded volume, of course, the shape of the molecule is the only thing that matters. But in reality, if the interaction has both steric and non-steric components, of course, by taking this average, the steric component will surface, and the average Hamiltonian will, in a rather indirect way, be affected by the shape of the molecules. And all right, something about this will be, I hope, will be in more detail presented in Andre's lecture, I think, tomorrow. All right, so we come back to this major player of our theory, which is the average Hamiltonian, and I repeat the main points which I already addressed. So H, which is our symbol for the average Hamiltonian, depends only on the state of the interacting molecules, and for rigid molecules, H is ultimately a function of their relative orientation. And so mathematically, what do we have at the end of the day? Well, we have a mapping from the orthogonal group into the real. Orthogonal group means that we essentially imagine that fixing one molecule, of course, there is a certain degree of invariance here. So the only thing that matters is the relative rotation of one particle relative to the other. And so what we have from the mathematical perspective is just a mapping defined on the orthogonal group that takes values into the real. And OV is just, V is a three-dimensional translation space. So it is a real valued function on a group. All right, but it has some peculiarities. It is not just a generic function. Of course, if we imagine that the two molecules are completely interchangeable, so one molecule is exchanged into the other by simply taking the inverse of the orthogonal transformation. So it simply means, if you think about it for a moment, it simply means that if the two particles are completely equivalent and they can be exchanged without harming the interaction, then it means that H hat of R must be equal to H hat of R transpose, because transposing the tensor in this group amounts to taking its inverse. So again, this is another peculiarity that this mapping has to have. And now we see immediately that as a consequence of these two properties, which are very basic ones, there is a kind of theorem, a kind of proposition that we can prove. Of course, we can take R close to the identity. So we might imagine an infinitesimal orthogonal representation. And this being a Lie group, we know that the generators of this Lie group are all skew-symmetric tensors, so it means that I can approximate locally these orthogonal transformations as the identity plus epsilon w, where epsilon is any skew-symmetric tensor. Now, what do we learn from the previous property? Well, when we transpose this, we get I minus epsilon w, and so this means immediately that if the two molecules are completely interchangeable, then the identity must be a stationary point for H hat. So it means that when the two molecules or the two particles are alike, the function that describes this average Hamiltonian must be stationary at that point. It is necessary. Of course, this might be minimum, a local minimum, might be a global minimum, might not be a minimum at all, but yeah, it is certainly a stationary point. So we introduce this terminology. We say that H hat is globally attractive if at the identity it attains its global minimum. This is often the case, but not always. It is the case in a number of examples that I will show you later on. It is certainly the case in Meyer-Zauppe's theory for liquid crystals. It is the case in Streley's theory for biaxial liquid crystals. It is the case in many situations, but not in all situations. So this we need a term just to name this situation. All right, but this is not the end. This function H hat has also other properties. Suppose that there is a number of transformations that do not affect the interaction. They might affect the molecule, they might affect the shape of the molecule, but they do not affect the interaction. So if such a transformation exists, we can easily prove that the set of all these transformations is a group and must be a subgroup of the orthogonal group. And so a symmetry group is defined by the members. Its members are defined in this way. These are the members S, such that when you, before rotating one molecule, you apply this symmetry transformation first, and then you rotate it. I'm just using rotation as a kind of general term for an orthogonal transformation. A full orthogonal group is involved here. Then the interaction stays the same. So this means this is a formal way to describe the presence of symmetry transformations. So again, I am led by the notion of interactions. So what is really the major player in this presentation is the interaction H hat. So what doesn't change is the value of the interaction. The molecule might get changed in its shape, but if it doesn't, such a change doesn't affect the interaction, then I call it a symmetry group, a symmetry transformation, and the collection of all these transformations is a symmetry group. And then I can, by using this formalism, I can introduce the notion of polarity. But for me, polarity is simply defined in this way. I say that the interaction is said to be polar if the total inversion, if the direct inversion is not a member of G. I say that the interaction is apolar if the total inversion is a member of G. All right. Now, of course, it would be nice to start this presentation by introducing dipolar interactions. And actually, this was my first choice. But then I changed my mind. I changed my mind because, as Tim reminded all of us, it is, well, proved, experimentally well proved, that dipolar interactions do not suffice to justify the liquid crystal collective behavior. And so I started by considering an apolar interaction. So for the moment, I consider an interaction which is such that polar terms are ruled out, and in this I apply my previous definition. And so this means, in physical terms, it means that the behavior, the collective behavior of molecules, is not the one that gives rise to the liquid crystal behavior, is not prompted by the alignment of permanent dipoles in the molecule. So I am assuming at the moment that the permanent dipoles in all the molecules are completely absent. Of course, we could come back to this issue later on. And so we can develop a formal theory based on a quadrupolar approximation, H hat 2, this 2 stand here for quadrupolar, of the average to the average Hamiltonian H hat, which may be justified in terms of an interpolation. And if time permits, as I already announced in my introduction, I will show you one way to justify the approximation to the Hamiltonian in a way of interpolating. This is a very old idea, actually. There's nothing original here. And this is an idea which I got from Streley's paper, 1974, Streley's paper on biaxial nematics. He wanted to, at that time, of course, nobody knew about Streley's potential, and he wanted to justify the interaction potential between the pair potential between two biaxial molecules. I'll show an example later on. And he had no clue. And so he said, all right, why don't we imagine that this interaction is simply given by excluded volume interaction? So it took 2 boxes, and he wanted to compute the excluded volume of these 2 boxes, taking any possible relative orientation between these 2 boxes. This turns out to be nowadays is a nice and simple exercise, but at that time was not doable. And so he said, I don't know how to do it. And then he got this very clever idea. He said, at the end of the day, what I need is only the quadrupolar approximation to this interaction. And so why don't I take a quadrupolar function, the way I'm going to do in a moment, and I determine the coefficients of this general expression by simply requiring that the quadrupolar expression of the interaction potential meets the values of the excluded interaction that I can compute. And those which I can compute, Streley said, are the simple ones. When I take 2 platelets face to face or edge to edge. And this turned out to be a wonderful approximation. All this paper actually is based on this approximation. And this is a quite general, and in my view, it is quite a promising idea, which actually we applied in a different context. So the idea is that you renounce the complexity of the function h hat, and you introduce a simplified function which has the same symmetry, and on top of it, to make it realistic, it interpolates the value of the real, and of course, quotation mark, the real interactions in those configurations that you are able to work out explicitly. I know this might sound at the beginning a little bit vague, but I'll try to build on this idea, and I'll try to corroborate this idea if I can at the end of my presentation. Of course, you might follow this advice. I know simply tell you that there is a way, and which has been used in the literature already by this interpolating means, or you may not follow this advice. Of course, it's up to you. But once again, you should be aware that if you do not follow such any guideline, you might renounce following any guideline to be on your own, then you need to be ready to face a number of control or of model parameters that symmetry allows, but which are not easy to control. I mean, in Mayer-Zauber theory, which I will review in a moment, is an astounding example, because you don't have any model parameter in it. But already Straley's theory for the biaxial interactions, as we'll see in a moment, has already two scalar parameters. And still, even with two simple scalar parameters, the mapping the properties of the interaction and mapping the possible phases that would be predicted on the basis of those two parameters is not an easy task. Even two parameters may drive you mad, or I should say, may drive me mad. All right, so how is this conceived? Well, formally, H2 hat is written in this form. This alpha ij ej prime, and ej prime is simply here a shorthand for r ej r transpose. I mean, the idea is that you simply imagine one molecule and the rotated molecule, and then you take the inner product between the representative tensors, the representative quadrupolar tensors that embody the symmetry. We'll see in a moment how the symmetry can be embodied in these tensors. But this is all you can to do. You have just a basis of traceless second rank tensors, and because you live in this three-dimensional space, and this alpha ij are the scalar coefficient. So which need, of course, there are many, as you see from here, because I and j run from 1 to 8, and this is the most general quadrupolar expression of the Hamiltonian H hat. Of course, it has all the properties that it has to have, and we call it quadrupolar simply because it is built in terms of second rank tensors. Well, the fact that they are traceless, and the reason why there are only 8 and not 9, is simply due to the fact that you can easily prove that if you do not make them traceless, the only thing that changes in this expression is just an additive constant. And since the Hamiltonian is always defined to within an additive constant, you can simply trash it in the bin. So this is the most general quadrupolar expression that you can get. And as you see from here, there is no need to require these tensors to be symmetric, and these are generic second rank tensors. All right, another way, which is just the same, would be, which is, more appealing to people who have been have had experience with elasticity theories, would be to say that this H2 hat can be written in this form as a quadratic function, and this f is a fourth rank tensor. It is a tensor that linearly converts second rank tensors in second rank tensors, and this is a formal way to represent this fourth rank tensor. So these interaction coefficients alpha ij actually can be regarded in two different ways. One way was in my previous slide, which is this way, but the same coefficient can also be represented as entries of this fourth rank tensor. But at the end of the day, this is it is an 8 by 8 matrix. And again, we require the invariance under molecular exchange, which makes this tensor symmetric, and consequently these alpha coefficients such that alpha ij is equal to alpha ji. So this 8 by 8 matrix is eventually symmetric matrix. And again, we can easily prove that if there is a symmetry, a symmetry group G, then such a symmetry group is characterized in this way. So it is such that all its members commute with the tensors that you have selected to represent your quadrupolar approximation. So the lesson that you learn is that the quadrupolar approximation of a symmetric interaction can be constructed only in terms of second-rank tensors that commute with the members of the symmetry group. So again, this is a guideline which comes only to the construction of the quadrupolar approximation that comes only from symmetry. And of course, you can elaborate a little bit more on this linear algebra infrastructure, and of course, you can represent, now that we have learned that this alpha ij is a symmetric matrix, you can represent it in terms of eigenvalues and eigenvectors. And this is, of course, the modal decomposition of the matrix alpha ij is going to be a modal corresponding decomposition of the interaction, and here it comes. And we call A, and now these are going to be the ingredients on the basis of which we construct our order tensors. These A's are formally constructed by taking these linear combinations of the allowed tensors. Of course, these tensors EI, they are a basis and they can be chosen completely freely. Now, what really embodies the symmetry of the interaction are the tensors AL, and these tensors AL, as you see from here, are constructed in terms of the eigenvectors of the interaction matrix alpha ij, and this epsilon L are the corresponding eigenvalues of this modal decomposition. So at this stage, you have found a new way of writing your quadrupolar approximation to the interaction Hamiltonian, but in terms of things which in different theories, for example, are called the symmetry adapted tensors. So, but in a way, this is a kind of constructive algorithm that whatever basis you take at the beginning will lead you to write the Hamiltonian in terms of physically significant properties. And at this stage, you simply say, all right, the ensemble averages of these constituents that have been already, that have gone through the scrutiny of symmetry are the order tensors. So these are the molecular, so to say, ingredients, and the ensemble averages are the order tensors that result from this interaction approach. Of course, at the end of the day, you can even count how many of these tensors the theory allows you to have, and of course the number is given by the rank of the matrix. So at the end of the day, this algebra tells you that, at least tells you what is the number of the independent and physically meaning order tensors that you can build out of it. All right, again, some terminology. If all these eigenvalues are negative, this H2 approximation, this quadrupolar approximation to the average Hamiltonian is called fully attractive. If some are positive and some are not, then we call it partly repulsive. And the idea is very simple, because the moment you see, if you go back to this representation here, the negative eigenvalues, the negative epsilon, would make the corresponding eigentensors to be aligned, because of course, if there is a minus sign here, you gain energy, so you reduce the energy by making AL and A prime L aligned to one another. On the contrary, if the coefficient is positive, then the corresponding term would be minimized when the two tensors, one for one molecule and the other for the other molecule, would be orthogonal in the inner product, of course, introduced in the space of tensors. So, I mean, again, this is a property that applies to the single term. At the end of the day, we know from general properties that this H2 hat must have a stationary point at the identity, and then by combining different signs of the epsilon, you can force H hat to be minimized at R equals the identity. So when the two molecules are parallel to one another. But as I said, this is not necessarily the case, and this representation actually covers all possible cases that can be represented by a quadrupolar interaction. So this is just to explain the origin of the terminology. I'll give some examples. It is after lunch. I think that even my general theory has been too long, and it has been an obstacle to your digestion. So I go now to a number of apolar interactions I would be interested in. Of course, this is the capital example. It is a Meyer-Zauper interaction. Well, in this case, the G group is just a D infinity H. This is just a cartoon to represent schematically the symmetry. And then that's the answer. In the symmetry, this is the only possible quadrupolar interaction between these two objects. And this Q tensor is a molecular or tensor, which is defined in this way, which is uniaxial along M is the long axis of the molecule. Q prime is written this way, and M is a molecular axis. Well, in this case, if U naught is positive, then this is globally stable according to our terminology. And of course, by applying routinely this theory, you simply come up with the idea that there is one single order tensor, and this order tensor is the tensor which is at the basis of Landau-Degen theory. All right, Straley interaction. I have already mentioned this, but very, very quickly. I think that Chuck in his lecture will talk more about it. Then this is the cartoon representation of the symmetry group. This is the description of the symmetry group. It is a D2H, and then all of what you get is precisely this. By applying the theory, this is the most general form, which is compatible with the general principles that I have already laid down a minute ago, and a new member, of course, comes into the club, and this is E tensor E minus E perp tensor E perp. This is again another molecular tensor, and E perp and M, for some reasons I don't see the labels here, but M would be the major, what you simply call the major molecular axis. E and E perp are the two axes on the plane orthogonal to the major molecular axis. And again, you can work out this pair of inequalities that tell you that this H2 hat is globally attractive. Of course, away from this region in the gamma lambda plane, this interaction is perfectly well defined, but it is not globally attractive. So it is not globally minimized by the configuration in which the two molecules are one parallel to the other. And within wherever lambda is less than gamma squared, then this interaction is partly repulsive in the according to the terminology that has been introduced a moment ago. And I hope that Chuck will give more details about this. I hope. Again, now there are two quadrupolar tensors that come directly from the theory. One is the old protagonist that we know, and there is a new player, which is simply this biaxial tensor, which is the ensemble average of this molecular biaxial tensor. All right, there is still another case, C2H symmetry. These are S-shaped molecules. The group here is a little bit more complicated, and it is generated, it is still apolar because you see minus the identity is here, and it is generated by these three tensors. R1 is a reflection relative to the plane that contains M2 and M3, and it is formally defined in this way. M2 and M3 are vectors on this plane. M1 is coming out of the plane, and this is this is a pi rotation about M1. Sorry, it is the rotation about this axis coming out of the plane by pi. And now there are new ingredients, and W1 is this skew-symmetric tensors, which is defined in this way. And actually, if you go through the same procedure once again, you find a rather prolification of terms, E1, E2, and E3. Well, E1 is expected. E2 is expected as well because it plays the role of the B tensor in the previous case. And E3 and E4 are the newcomers. And you see that one of these, actually E4, is skew-symmetric. All others are symmetric. And again, this is a general representation of the admissible quadrupolar energies. We call this the dispersion coupling matrix. And this, well, the coupling between W1 and Wy prime, I remember, keep in mind that W1 is skew-symmetric, so this is a kind of way to discriminate the behavior of the symmetric tensors from that of the skew-symmetric tensor. And this term, I call it pseudo-dipolar, and the reason is that can be written, if you call M1 and M1 prime, the two axes of the two vectors, tensors W1 and Wy prime, you can rewrite this inner product between tensors as this inner product between vectors times the determinant of the transformation. And this, of course, is a pseudopolar because if you if you take R to be minus the identity, this inner product doesn't change. So it is not just the inner product of two vectors, but it is the inner product of two vectors corrected by the determinant of the transformation. And this must be the case because there is no polarity in this case. But of course, this is interesting because this gives rise to a new term, to a new coupling. And actually, this has been exploited by Misha in one of his papers with Gorkunov, and it has precisely this new term coming out, or at least this is my rendering of the new term he has in his theory. Quadrupolar tensor theory. So now we know how, in principle, we can construct a theory based on the information we presume to have on the basic interactions of the molecules. And I've given three examples. Of course, things get more and more complicated as the symmetry, of course, of the molecule, and actually I should be more accurate. The symmetry of the interaction becomes poorer and poorer. All right. So we come back to the first example. And in this case, our order tensor is simply defined in this way. M is a molecular axis. So what I have in mind is a simplest Meyer-Zauper interaction. And of course, this is already complicated in its own because there is no guarantee at the end of the day that once you have taken this molecular average, the tensor you get is uniaxial. Because what you are taking here are averages of uniaxial molecules, but the same vector changes from one molecule to the other. So what you are taking here are averages of symmetric traceless tensors. So what you can expect to get is just a symmetric traceless tensor, and it is here. Not only this, but if you just play around with the eigenvalues, if you prove, it is easy to prove that the eigenvalues of this tensor must range into the interval minus 1/3 to 1/3, and that's easy to get because this is a symmetric tensor, so it possesses an orthonormal basis, and so you can generally represent Q in this way. You introduce 3 eigenvalues, which are lambda 1, lambda 2, lambda 3, 3 corresponding eigenvectors, and the only thing you know is that the sum of the 3 eigenvalues must be equal to 0. So because the trace is a linear operator, and the trace of all these tensors that you are averaging upon is 0. So at the end of the day, the trace of the resulting tensor must be 0. And of course, there might be biaxial states produced by that uniaxial interaction. So I'm going back to the father of all these interactions, which is the Mayer-Zappa interaction. So the description of the interaction is uniaxial, but nevertheless, the average can be biaxial. And so the basic ingredient of our continuum theory might be biaxial. Of course, if 2 eigenvalues are equal, and this is a uniaxial limit, this is an explicit representation of Q, and we have seen this several times. S is sometimes called the scalar order parameter and ranges in between -1/2 and 1. But if we require that 3 eigenvalues of Q are all equal, then there is no choice, since the sum must be 0. Each eigenvalue must be 0, and so you represent what is, for all intents and purposes, called the isotropic state. You can also measure the degree of biaxiality, and this has been introduced some time ago, and it's simply a scalar measure of the difference between the eigenvalues. It is 0 for all uniaxial tensors. It is bounded by 1 in the case of maximum biaxiality, and the maximum biaxiality is achieved when the determinant of the Q tensor is 0. This is just one algebraic property. All right, there have been several biaxial representations for the Q tensor, and there are plenty in the literature, and I'm just picking up one which is not my own, just to be unfair to myself. And so this is the SP representation. So this, of course, is the most general representation of a biaxial tensor. Of course, if P is 0, this is uniaxial. If P is different from 0, this is biaxial. Of course, in this representation, I've chosen E1 to be E, E2 to be E perp, E3 to be N, so that these 3 vectors, E, perp, and N, are all orthonormal. And in the lambda representation I used a moment ago, this would be the transliteration formula. All right, I represent the invariance of the tensor in this fashion: trace of Q squared and trace of Q cubed. And now what do I do with it? This is my basic ingredient. I want to build a continuum theory, and this has been done in the past. And so there are 2 ways. I need to take into account 2 different sources of distortion. One is what I call the condensation energetics, so the energy that comes or that needs to be spent in order to build the phase, and a distortion energetics, which is the one that goes, as Oleg showed with his fingers, in his fingertips, the one that goes into producing a distorted state in space. All right, this is the Landau-Degenbach potential. So the idea is just, as Tim said, we simply start with an expansion. An expansion, of course, we need to build a function which is a function of the invariance, trace of Q squared, trace of Q cubed. These are the only invariants that matter in this case, because trace of Q is equal to 0. And what we do is simply write an expansion, a Taylor expansion to that effect, which would mimic the phase, the formation of equilibrium phases. All right, these constant A, B, and C are chosen in such a way that B is always, and B and C are positive, and A and independent of temperature, and A is this linear function of temperature. Of course, this is the easiest choice that has been made, that has been proposed in order to recover the energetics of a phase formation. All right, I wish just to do some algebra here. I introduced this sigma squared factor, which is just comes from this definition. And then if I do this, I obtain if I assume that S is positive, I can express S in terms of sigma and P, and I can rewrite my FB function in terms of sigma and P. It's just a change of variables. Instead of using S and P, I use sigma and P. What's the reason of doing this? Well, the reason for doing this is that since B is always positive, if you freeze a sigma for any given value of big sigma, you see immediately from here that FB is minimized by setting P equal to 0. So this is the kind of elementary proof that the potential that you have introduced, since B is positive, and of course the sign here is crucial, since B is positive at equilibrium, when it is minimized, it imposes P equal to 0. So according to the picture that I have been drawing, at equilibrium, biaxial phases would disappear, and only uniaxial phases would be produced by that function FB. And of course, then this I can, in this case, sigma and S coalesce, and I can rewrite my potential in this form. And this is a picture that has been shown in all books. And so this is how this uniaxial potential now behaves. But mind, the potential is defined on a biaxial manifold. So it is a function of S and P. But what we know, we're just looking at the section at P equal to 0. But we know that in the absence of any other frustration, it is minimized by P equal to 0. So we know that the graph of this function will grow out of this plane, but on the plane P equal to 0, it is minimized by the least value in S it can take. And this is the behavior of the minimum and of the minimizer as the temperature decreases. This T double star is sometimes called the superheating temperature. It is a temperature at which there is only one minimum, and the T&I is the transition temperature, kinematic isotropic temperature, at which the value at S equal to 0 and at S different from 0 of the two minima is the same. And then this is the super cooling temperature. It is a temperature at which a minimum is lost at the origin. All right, now it is just a kind of simple exercise to compute explicitly how these equilibrium points depend on S, on B, and A, and C, and since big A depends on temperature, how they depend eventually on temperature. And I don't think there is much of interest here. The only point I want to make is that here we can just relate to temperature all these values. And again, the reduced temperature, which is usually introduced in this fashion, and it is such that the nematic isotropic temperature takes place at this 8/9. This is a very common, and it is done by many authors, just to reduce the temperature to a dimensionless parameter. And wherever theta is less than 8/9, the bulk equilibrium value is this S plus, which is related explicitly to temperature by this very simple relationship. Of course, there is also an energetics related to the distortion, because so far I have considered the homogeneous phase, and some energy has been spent in order to produce the energy with the least phase. But of course, I should allow for distortion in space, and as Oleg pointed out, there is energy and work to be done, energy to be paid and work to be done in order to produce dispersion. The idea is that there is an undistorted state, And the distorted state actually is a macroscopic revelation of the property of this h hat function once again. If the h function is globally attractive, as it is ours, then the interaction energy is minimized when q is equal to q prime. So this identity of q and q prime at the molecular level reverberates into the macroscopic realm in this property. So once again, this is a property that we inherit from the function h hat. And so proposals have been made by Landau himself, by Lejeune himself, to write the most general quadratic function in the gradient of f, in the gradient of q, at the most quadratic and frame indifferent. If you require the function f to f, the density energy to be quadratic in the gradient and independent of the observer, this is the most general expression you can get with only 3 elastic constants. And in Cartesian components, this would be the explicit representation of these individual terms that I have introduced. And as was proved in 1987, if you want this to measure the distortion from the uniform undistorted state, then if you require this to be a quadratic positive definite form, then you need to impose these inequalities on the elastic constants. All right, so at the end of the day, the free energy function null can be written in this form. Now there's something that that expresses the energy penalty in the condensation and the energy penalty related to the distortion. And of course, you pose a variational problem for this functional, and it might well be that the frustration differently imposed on your field Q, either by boundary conditions or by the interaction with external fields, will eventually result in cases where in configurations where inside the bulk region B, Q vanishes. Well, this we know has to be interpreted as a loss of ordering, and so we interpret it as the occurrence of defect within this generalized theory. 5 minutes, I'm just come to a close. Of course, there have been many critical remarks, and I will only pose on one, which I personally find very promising and very enlightening. Of course, the problem is that you have here a polynomial potential Fp, and there is no guarantee that all sources of frustration that may be imposed on your system will lead your equilibrium Q order configuration. Now, the Q is a field, and it minimizes the overall free energy. So there is no guarantee that somewhere the eigenvalue of this Q tensor will exceed the physically justified bound, which is between the interval minus 1/3 to 2/3. And because the functional is just polynomial in the Q tensor. All right, this is an idea which I personally got from Jerry Erickson. I was sitting in his classes in Minneapolis at the time when he was writing this paper. It is a paper on liquid crystals with the scalar order, variable scalar order parameter. Well, it is a very interesting paper, 1991. And I was sitting there. Jerry had this habit. He had this very nice seminar, and during the seminar he was simply presenting his own work, which would be published maybe 2 or 3 years later. I sat in his class in 1985. The paper was published in 1991. So he gathered all comments and remarks. And in one point, I mean, one remark of his really stuck in my mind. He said, all right, we need to imagine that this potential that we insert here should be better than Landau-Degen's, because it should really it should blow up near to the configurations in which the eigenvalues tend to exceed the physically justified interval. And I think that this went also into his paper. So of course he simply laid down a number of requirements to the FB in his specialized theory, but of course being valid for his specialized theory, these requirements should be valid also for the less specialized theory, which is the one we are aiming at. All right, there has been an attempt made by John Ball and Apala Majumdar recently to reformulate this potential FB in a way which, of course, I cannot recapitulate in a few minutes, but which tends actually to bridge this gap between, which I only attacked from a formal point of view, between the Mayer-Zaupen-Minfield theory and the continuum theory. And there are a number of properties I wish to finish with. I really don't know what form FB has to take, but certainly there are a number of requirements. Again, I'm looking from this quite distant formal point of view. It must be frame indifferent. Frame indifference means that if I change my point of view, the potential should be the same. And of course, this means in technical terms that it must be an isotropic function of Q. Of course, if this is the case, as a consequence, the gradient of this function must be an isotropic tensorial function of Q, whatever FB you want to insert. And then you look at these classical theorems called sometimes reduction theorems, and there's this nice classical representation theorem that says that if you have a tensorial isotropic function of the tensor Q, it must be represented in this form. Phi naught, phi 1, and phi 2 are symmetric functions of the eigenvalues of Q, and this is a very old result by Rivlin and Eriksson, which was proved in the 3-space dimension. It has been generalized, and the general expression for this is actually in Noel Truesdell's article in the encyclopedia. But then, sure.
So I think I missed what the gradient operator is there. Is that a derivative with respect to Q? Or
yes, this is a great. Yes, this is a function.
With respect to space. Okay.
Yes, not with respect to space. Sorry, being this a function of Q only, I thought that this. All right. So I come back to this. Now it means that I'm simply rewriting the point. So this would be the general expression. I really don't know what FB is, but whatever it is must have this. The gradient must be this, have this expression. And if I require a point Q to be at equilibrium, this must be the case. So at equilibrium, this must be valid for the appropriate function phi naught, the appropriate function phi 1, and the appropriate function phi 2, which reflect the specific FB that I have introduced. Of course, since Q has a basis of eigenvectors, I can equivalently write this as a triple of equations in the eigenvalues. But you see, this is a quadratic equation for the 3 eigenvalues. And of course, there cannot be 3 unequal roots for this quadratic equation. So this means that the solution to this equation must possess 2 equal eigenvalues. So it seems to me, and this is a challenge to you to prove me wrong, it seems to me that the nice proofs that have been put forward by Fatkulin and Stratikov and Zhu, Wang, Forrest, and Wang again, to the same effect, that at equilibrium, the configuration of a Landau-Degen theory must be uniaxial in the absence of any other frustration. Actually, it seems to me that it is just a consequence of frame indifferent and isotropy, and which must be valid for all possible choices of functions FB. All right, so I thought about this proof. I couldn't, it is too simple to be true. So it is a challenge for you to prove me wrong. I would be delighted to be proved wrong on this case, as I was on many other cases. Thank you very much.
Well, thank you very much, Epifanio, for a very nice conducted excursion through very important foundational material, ending with a challenge. So we now have a tea break. Sorry, is that a question there? Yep.
Just a question. So do you think that your last statement explains why the people doing experiments have so many difficulties in identifying the biaxial nematic phase?
Well, not quite. Not quite, because this applies only to the single tensor order theory. But you are not far from the point, because similar consequences should be drawn also for the dual tensor theory. And so I don't know yet the answer. Could be that yes, but I've not done the attempt for the other case.
What is the geometric content of the fact that for the S-shaped molecule you have a skew-symmetric the fourth one of those second-order tensors is skew-symmetric?
Because it is generated by this rotation. If you just do a pi rotation, then...
Yeah, that's clear, but what is the consequence of that? I mean, if you look at the order that such a system of molecules has, what would be distinctive about it that tells you that?
Yeah, it depends on the sign. At this stage, it depends on the sign of this coupling parameter lambda. It could either favor in-plane configuration, or it could disfavor it. So it could be an incentive for the two molecules to stay out of the plane at equilibrium. But maybe Misha knows much more.
There was another. Yeah.
Epifanio, you presented the whole lecture about tensors, I think, without once mentioning directors. Should I understand from that your opinion is that we can spend the entire meeting working with tensors and never mention directors, right? Or is there any reason to think about directors?
Well, I don't want to be too imposing. But I think that this is my dream. Of course, there are situations in which you can prove that your tensor texture can be unequivocally represented by a director texture. And then you can really use the two descriptions in the same way. Equivalently, interchangeable. But there are situations in which the two representations are not equivalent. I mean, in terms of fields, you cannot, well, there is no a one-to-one correspondence. There are topological abstractions that do not allow you to convert a tensorial field into a vector. So to be safe and to be on the safer side, then I would use this tensorial.
Which was always.
Okay, thank you very much. I think it's time to.